Good morning to all. So my second lecture will be current scenario of dye-sensitized solar cells, modifications and large scale production. That is my second topic. So Dr. Jegadesan will talk about organic solar cells more. So I will talk about Dyson solar cell. Also I can give another lecture on organic solar cells, what we are doing later actually. So solar cells, maybe now we are in the third generation solar cells. First generation, second generation, they start in the year 1954, and then people are doing a lot of things, modifications in solar cells. So we are modifying things in our lab conditions according to Indian scenario and making a solar cell in our place. So India is a very good country. We have a lot of sunlight. We can see that sunlight, heavy sunlight, okay? Compared to any country, we have 365 days in a year of sunlight. So lot of sunlight will be there. If you go to Germany, Europe country, the sunlight is very, very less. They have maximum of 2 months to 3 months will be sunlight. But here we have enough sunlight actually. So current we need actually, global power demand is compared to terrestrial sunlight is very much small. You can see the sunlight will be very much small actually. We demand actually. Yesterday night also a lot of power cut because of everyone put AC. So we have a lot of power cut actually, okay. So we see in our country PV installations very minute. We have only minute actually. So that's a scenario. We have enough sunlight, but our PV installations, solar photovoltaic installations in our country is very, very small. But at present, lot of installations all over the world actually. If you see any institute, we have mostly used the PV installations. In our institute also, all the lecture are with the PV installations actually to get good scenario. Okay, this we talk about your sunlight. So how much earth we get the energy actually we talk about. Earth receives the energy is enormous 1.75 10 to the power 17 watt. That's the energy we receive from our country. Okay, that's the energy we receive from our country actually 1.75 10 to the power 17 watt. You can see. So which 47% of the energy will be from solar light. We can say solar energy. 47% will be solar energy. So we can say the energy demand for about 70% actually between 2000 to 2030 will be energy demand only 70%, that will be 4.4 10 to the power 20 joules. We can say we can produce this much energy in a sunlight in a 1 hour. We have, because we have enough sunlight, in a 1 hour sunlight we can produce this all this demand actually. So we don't have any power shortage, but we are not doing this one. So we are now focusing this solar cells in this context actually, okay. So solar cells are, we can convert into different types. That's called first generation. 1G is called first generation solar cells. Mostly people use bulk silicon solar cells. Whereas after this one, people move to second generation solar cells where they use the thin film solar cells like cadmium telluride and CIGS etc. material, gallium arsenide material actually. But these materials are somewhat expensive materials, so that also drawback actually, okay. Then comes, we are at present third generation solar cells where we are doing a dye-sensitized solar cells and organic solar cells. These are the one we called as a third generation solar cells. So dye-sensitized solar cells starts in the year 1989. The first paper comes from Great Cell. After that only we have enough work will be going actually. And organic solar cells people are doing actually. So this is the scenario we are now going to talk here. First, third generation solar cell more in depth actually. So in this, the first lecture I will give about the Dyson solar cell. Maybe Friday my lecture will be organic solar cells. So what is Dyson solar cells? What is the concept actually? Okay, what we can use. If we say dye, immediately you can ask, if you are a chemist, you can say, sir, we have a dye called phenolphthalein, methyl orange, okay, or rhodamine B, or malachite green. Sir, why not we can use such dyes? That dyes we can use for solar cells. Yes, we can use it, but the lifetime of such dyes are very, very poor, therefore problematic actually. And also, the dyes can degrade by sunlight illumination. So, we cannot use such dyes for our solar cell applications. Therefore, we need a special dyes that's called your dye-sensitized solar cells. In the case of dye-sensitized solar cells, a dye is called art. For example, a human being we have, human being art is very important. Okay, same thing for dye solar cell, a dye is most important. So how to choose a dye, that's the topic we have to talk about here in this context actually. So this is the solar cell modification technique. and we will demo this one on Thursday afternoon actually, how to make the solar cells actually, okay. So in this concept, first we have a TCO. TCO is called transparent conducting oxide glass. So transparent conducting oxide glass is a glass where normal glass plate is not conducting. To make this glass conducting, we have to coat fluorine doped tin oxide or indium tin oxide. That material has a good conducting power, so we have to prepare that material. So, or in general, this material is available in the market. We can buy this transparent conducting oxide glass plates from the market actually, which shows some resistance actually. Okay, that's the first part. Second part, we have to need a semiconductor. Semiconductor is the one we need, particularly TaO2. Some people use zinc oxide, but mostly in the case of solar cells, we use TaO2 semiconductor. And TaO2 is a semiconductor which has a band gap of 3.2 electron volt, which can absorb only UV light. It won't absorb any visible light. So the TaO2 we have to coat this by Dr. blade technique or screen printing method. So we have to do one by one. So coating of TaO2 on the transparent conducting oxide glass, that's the second method actually. Third, once this TaO2 is coated on the surface of the dye molecule on the glass plate, we have to coat the dye molecule. So dye molecule is particularly a ruthenium dye, actually. So this complex is more stable. This complex is more stable. Why? Because ruthenium complexes have undergo cyclic state, ruthenium 2 plus 3 plus state actually. So this compound has a power more than 10 years it is stable. Therefore, we have to use this dyes, metal complexes as one of the dye complex actually. So we have to coat this dye molecule on the TaO2 surface by dipping this coated plate over a night, or we have now instruments for this actually. We can coat by a method actually on the surface of TaO2. Once we coat, we can see this is the TaO2 particle, white color pigment, okay. TaO2 particles are there, and this we can view by AFM. We can see the surface morphology of the TaO2 coated plate. And then when you put the dye molecule, a dye molecule can adsorb on the surface of the particle. You can see dye molecule get adsorbed on the surface of the molecule actually like this. So it will be an adsorption phenomena. How this adsorbed actually, I can show structure of dye and we can explain actually. So this dye molecule has carboxy group is there actually, COH group is there, the anchoring group. The COH group will anchor on the titanium oxide as hydrogen bonding by molecular surface. So you can adsorb on surface the compound like this. Okay, this is a point. And other one is comes electrolyte. Electrolyte is iodine iodide. Generally, a good electrolyte is iodine iodide, but now people are modifying the electrolyte also, different polymer electrolyte, etc. That's a one. So we use a electrolyte iodine iodide. So in the one plate, we put TCO, TaO2 dye. The other side, we take another TCO, transparent conducting glass, over which platinum is coated. We have to coat the platinum on surface of this one by sputtering method or by different methods are there. So we can do say the sputtering or by spin coating or different methods are there. We can coat the platinum on surface actually. Why we choose platinum? Platinum is a good catalyst for this reaction actually. Once these two glass plates are coated, then you can put like a sandwich, you know, a bread sandwich. You can put like a sandwich one above the other, and then put the holes on the plate, and then fill your electrolyte iodine iodide. That's your solar cell can be manufacturing. So what happened now? To make a solar cell, we need TaO2, particle, dye, art of the solar cell, platinum, electrolyte. So this is the general Dye-sensitized solar cell available in the market, and we have also coated in the glass plates, as well as we have also coated by a thin film. This thin film will be coated in Australia, but we have coated in the glass plates in India. So they will be flexible. We can see the flexible one, so we can do maximum. This is the one actually. So this glass plate we can do in our system, and we can do efficiency can be calculated actually. That's the one as thin film solar cells. Okay. So what is the important I told? TaO2 particle. Sir, if we, instead of particle, if I make a TaO2 different morphology, what happens? Instead of this ruthenium complex, I choose different dye, what happens? Instead of electrolyte iodine iodide, I can choose another material, what happens? And last platinum, I can change to different one, what happens? So we want to see one by one in the next 1 hour talk actually. Okay. So this is your TaO2. So you can see the white pigment. So you can take it and brush it. Generally, we can say Dr. blade technique, we can brush it actually, TaO2. And dye, this is a dye molecule. You can see a dye molecule I said carboxy group is there. So this carboxy group will be anchored on the TiO2 surface, we can use. And this is the TiO2 SEM image. You can see all the C or particle actually, okay. And this is your liquid electrolyte, iodine, iodide. That is the one we have actually. So to prepare this liquid iodide, we may use organic solvents, acetonitrile. In addition, we add your imidazole based compound. This is called your ionic liquid. We add your ionic liquid. Why? Because if you use acetonitrile as solvent, in the sunlight we put the acetonitrile can evaporate easily. Therefore, it become liquid can be evaporated. Then cell may die. To avoid this, we can use a ionic liquid. Ionic liquids have boiling point more than 150 degrees Celsius. So the liquid electrolyte won't evaporate even at temperature will be 70. If we go to South Africa, sorry, Saudi, temperature will be 70 degrees Celsius over there. If you put this ionic liquid, without ionic liquid, the electrolyte may evaporate. So we can avoid the evaporation of electrolyte by adding this ionic liquid compound actually. That's the important point. So a dye may be color, you can see like a kungumam, Indian kungumam we can have, same color will be there actually, this compound actually, okay. That's a dye molecule, which is a carboxy group, ruthenium complex with bipyridine carboxy group actually, and thiocyanate ligands actually there. So this is called N3 dye. This is the one they published in 1993 with efficiency of around 7 to 8% by Gates et al. Group. This is a known material, all these are known material. So what we want to do in the research actually, we want to change the TiO2 by particle, by different morphology, change the dye molecule, change the electrolyte, change the platinum, everything we have to change, and what happens, we want to see the efficiency can be, what happens. That's our research we are doing in our laboratory actually. Okay, so what is the mechanism takes place, how the dye-sensitive solar cell works actually. So we coat this transparent conducting oxide glass, TiO2, and TiO2 dye will be adsorbed one side. Other side counter electrode, TCO, platinum is coated here, and then inside we have electrolyte will be there here actually. So what happens here, when the dye molecule gets adsorbed by sunlight, we have put the sunlight, dye molecule get adsorbed by sunlight. So dye goes from HOMO to LUMO. We can see it goes from the HOMO to LUMO. Only band gap we can say conduction band to valence band to conduction band. But in the case of dye molecule, we cannot say conduction band, valence band. We can talk about only HOMO to LUMO. That is the molecule having lowest molecular to highest molecular goes. So it can jump from the ground state to the excited state. So dye molecule can go from the ground state to the excited state. So once the dye molecule goes to the ground state to the excited state, you can see the level of positions. It will be higher than the band gap of TiO2 conduction band. So it can give the electrons to the conduction band of TiO2. You can give the electrons to the conduction band of TiO2. You can see here, it can go to this one. This stage is very, very important here. This molecule electrons move to the conduction band. This is like a cat in the wall. You know, cat in the wall, what happens? It can go back or go front. So you can go this side or you can go other side. If we go to this side, we can get the current will goes. Instead of this, if it not goes other side, it comes to ground state of dye. So cell may not working, or it may react with your electrolyte. From this it comes to ground state, or from this goes to the electrolyte, then the cell won't work actually. So these two steps are very, very important. We have to avoid such steps in the solar cells. So jumping back to the ground state of dye or jumping back on reaction with the electrolyte should be a drawback of your dye synthesis solar cell. So we should be very careful while doing this fabrication technology, and your positions of your HOMO, LUMO, dye, etc. should be maintained. That's the important part of your work actually. You can get your solar cell. So once it comes to counter electrode, what happens? Your liquid electrolyte is iodine, iodide. So iodine to iodide can be change take place. So it can be jumped from ground state to excited state. So we can see here, it can go from this level to other level actually. So once again, the electrolyte can be undergo oxidation reduction and come to the ground state once again. So like these steps are going cyclically, so we can get a good efficiency source can be obtained. If you use phenolphthalein or dye, the dye can degrade, or such cyclic states are not possible. Or therefore, we choose a ruthenium dye which has lifetime of 10 years, approximately 10 years. It can be stable and give the electrons like this continuously. That's the advantage of your Dyson solar cell working phenomena actually. So I told, so dye can excited from the ground state to excited state. It's called first step. We can call this the first step actually, HOMO to LUMO. Okay, that's called electron injection dye to conduction band. The electron injection from the dye, this one, from the conduction band. Second step, electron recombination. We can see the second step, this one, electron recombination. So this dye return back to the ground state actually. So recombination. So this step is a dangerous step. Efficiency depends on this step. So 2 second step. Third step, dye regeneration. So dye can once again come to the ground state actually here. So that also drawback, dye regeneration with electrolyte. So that step also drawback actually. Fourth step, electron recombination with electrolyte. We can see this one, once again come to electrolyte actually. So these steps are dangerous steps in reaction actually. And fifth only, electron trapping the nanostructure. We can see electron can trap from conduction band to Fermi level to etc. jumps here and there actually and goes to the excited state. That's the phenomena of your solar cell. So your step 2 and step 4 is a dangerous step. We should avoid these 2 steps to get your good efficiency solar cell can be obtained. That's a working phenomena of Dyson solar cell actually. Okay. Okay. So what we want to do? We said TiO2 particle. So particle as problem, you know, if you talk about nanoparticles, electron flow inside this one, it may interact with the walls of the molecule and get delayed. So to make this compound delayed, so we don't want this one, we can make a TiO2 nanotubes. We can make a TiO2 nanotubes. You can see here. So you understand that if you are in a metro has separate line, electrons can go rapidly. Okay, same speed, the tubes, electrons can go without any problem. If here it goes, it can interact with the particle like this actually, and it can slow actually. For example, in the Diwali time, etc., when you go to the market to purchase actually, what happens, lot of crowd can eat you. You can walk for 10 to 20 minutes actually. Whereas normal time you can walk faster, same distance. So we can prepare a TiO2 nanotube in our laboratory instead of particle to get this one. Electrons can go faster. That's the advantage of your TiO2 nanotubes compared to particle. So we can say TiO2, this is a TiO2 XRD, almost same as your tube, same as your particle, no difference between TiO2 particle and TiO2 tube. But you can see the thickness of the film can be from the same vertical angle. So thickness will be, the particle will be like this here actually. So I can give some image. Okay. So that's the advantage of TiO2 particle. So what happened now? You can see the electrons can go rapidly here. So this is the advantage of TiO2 tubes compared to TiO2 particle, where we can get a good solar cells can be obtained. So that's the important point here. So good solar cells can be electrons can be tunneled like a faster way to get your system can be done. Okay. So this is the way we make instead of particle, we make a tubes in our laboratory or wires and make a good efficiency can be reached. This is the same image of your TiO2 particle, TiO2 tubes. So you can see the TiO2 tubes are open here as a point. Second important point actually, in the case of your tubes, you can see dye molecule on the surface of the walls as well as inside the tubes, go inside the tubes actually. Whereas in the case of particle, you noticed actually, in the case of particle, it will be only on the surface. It can only on the surface. So number of dye molecules absorbed will be here less compared to there. So that's the advantage here. Dye molecules are more, number of photons absorbed by the dye molecule will be more. Therefore, we can say that in this case, we have lot of photons are absorbed here. So we can get a good efficiency will be there. So that's the advantage of your tubes compared to your particle. That's the first part we can notice from this observation of the studies. Instead of particle, tubes are much better actually. Okay. Second point is dye. So I told dye is the art of the molecule. Okay. I said dye is the art of molecule. So what happens in the case of dye molecule actually? See, dye has to give injection time, electron injection time. Electron injection time should be faster. Very important for dye. It has to give the electrons faster. If you take a ruthenium complex, it gives the electron faster. Phenolphthalein, no. Methylalanine, no. That's the advantage here. It gives the electron faster. Second point, recombination time. It should not recombine. Electrons one given, not take back. That's very important actually. Once we given, is given. If you take back, what happens? Once again you become normal. So this is the case we can notice here. This is the case we can notice here actually. In the case of electron injection time should be faster, electron recombination time should be lesser. So this is the important part of the dye molecule. So why they choose the N3 dye? Because electron injection is faster, recombination time is less. So people are using that one and not the normal dye molecule like phenolphthalein, metal orange, etc. That's the advantage of your dye-sensitized. So how to tune the dye molecule? Very important here. We want to tune the dye molecule. How to tune the dye molecule? So we can make a more functional groups. So people are synthesizing dye molecules, different one. They call N3 dye, black dye, etc. You can see they change. This carboxy group they maintain. Previously they put SCN only one dye, N3 dye. They get the black dye here, put a different ethylene complex here once again. Change these two positions by different one. Or they can take a terpidine ligand or a carboxy group and they put different SCN. So we understand that it needs a carboxy group and dipyridine or bipyridine. These compounds should be absorbed for a solar cell. So we have to prepare this dye molecule like this, which are lifetime more, 10 power 8 turnover numbers. That means lifetime will be more, means you can stable for 10 to 20 years actually. That's the advantage of a dye molecule. Seeing the structure etc. in general, we want to modify in our lab actually. So we want to do some modification of a dye-sensitized cell in our laboratory conditions. So what we do, we take a bipyridine. So you noticed here, they use either bipyridine or only terpidine. But we take one bipyridine, one terpidine actually, okay. So one bipyridine here, one terpidine actually, and then chlorine or thiocyanate or CN. We change this functional group here, chlorine, thiocyanate, CN, and we prepare dye molecule, different dye molecule in the laboratory. So we also calculate the lifetime by laser method. Molecule shows higher injection time and less recombination time we notice from the laser lifetime methods. So this is a laser lifetime instruments. So we can see the compound shows higher injection time and less recombination time, and we make a fabricate solar cell size 1 square centimeter, and then we get the efficiency of voltage is 400 millivolt and 2 milliamps current we can get in a single cell. Very small actually. This is, we can see 2009. For example, we do this work in 2009. So they start this work in 1990. I just say 2009, after 20 years only we are doing in India, okay, that's why we call research. We are not doing research, we are called only research actually 2009. So we find that efficiency is still lower, we want to modify this one further and further actually and then do modifications. So while thinking these dye molecules, so we think very important here, the carboxy group. So one carboxy group are adsorb on T wood surface. So we want know carboxy groups are most important actually. So replace carboxy group, we want to prepare something. People use phosphoric acid also, but we say so one carboxy group here, one carboxy group here, like that actually. We can get two carboxy group we can prepare like a donor acceptor compound actually. So in our laboratory we change the dye molecule. We can see this is called metal free. Okay, what is metal free actually? The metal complex, people say metal complex are toxic, okay, corrosion actually. So how to avoid this component? So they can replace the metal by metal free organic dyes with a donor pi linker acceptor. They say is a donor pi linker acceptor. This is a donor molecule and this is a pi linker and this is acceptor. They prepare a compound with donor pi link acceptor and they get approximately 9% efficiency. So this is one donor, one pi linker, one acceptor is there. So this is another molecule, one donor, one pi linker acceptor. So you can see carboxy group is there everywhere. Carboxy group is everywhere actually to adsorb on surface of TiO2. So they prepare like this. Seeing this structure, we think they put only one carboxy group, one donor, one pi linker. We in our laboratory change the conditions. So one donor, one pi linker, one acceptor. Same side, one donor, same donor, one pi linker acceptor. So we have two acceptor in one donor. We prepared modifications. We prepared modification in a laboratory like these conditions. Okay, one donor, two pi linker, two acceptor. You can see we prepared like these compounds many, and we can do publication in our laboratory conditions. And this is we do in the year maybe 2010 or 2011 actually. We get efficiency of 2.3%. We get efficiency of 2.3% efficiency. So that's the scenario. The dye we can modify. We can get the modification dye one by one in our application solar cells actually. Okay, then we think, people may ask, sir, dye you are preparing, sir, why not we can prepare natural dye? Natural dye molecules like plant extracts. Some of the collaborators of botany department, and they asked me, we can give some plant extract, we can prepare solar cell actually. So this is called ivy gourd. In Tamil we call kovakai. So we take a extract from the ivy gourd and do this absorbance plot. Similarly, this is a flower. Generally in a garden we can find red frangipani. This flower also we make extract and we can see. When we see this compound UV light, the absorbance are found here. It mostly contains beta carotene and another form of beta carotene and etc. pigments are found. These pigments will lead to this absorbance. So these pigments can absorb light energy. From this we can calculate the solar cell. We can get efficiency. You can see the efficiency of very less. We get efficiency of very less actually, 1.31, 0.48. But lifetime also not good. So we see this is just for publication. We do it actually and get a small efficiency can be noticed. So next comes your Nobel Prize winner quantum dots. People can choose quantum dots. So we can see cadmium selenide, which has prepared different sizes. Yesterday I told your vase made up of different colors. Quantum dots, cadmium selenide, green, orange, red, blue. We can prepare different colors. So this we can make a solar cell and get efficiency. So maximum 14.32. We are tried in a laboratory, but some conditions we failed. So we dropped this material because cadmium selenide shows different color images. So we have some drawback when you do the solar cell absorption on the TiO2. So we dropped actually, okay. And also this pyro ligand is they use electrolytes, not iodine. They use pyro. The cost of material will be 55,000 rupees, approximately 1 ml. So we don't want to use the high cost actually. We dropped it in our laboratory, this preparation method actually, quantum dots. So Dyson solar cell, dyes are most important I told. So this is the concept. They prepare solar cell and get the efficiency up to 44%, we can say. 44% they can observe in this case actually. Okay. Second point, first TiO2 I changed, second I changed your dye. Now come your Dyson solar cell, third point electrolyte. So electrolyte is very important here, iodine iodide. With low cost, we can prepare iodine iodide and get maximum of 11% in the laboratory conditions actually. Drawback is here, the liquid electrolyte can leakage. When you put the solar cell, it can leak out from the cell and cell may broken actually. We will show the slides maybe Thursday afternoon how to make this one actually. So with liquid electrolyte etc. So they can get peel out from the system actually and the solar cell can be dyed actually. So we don't want such one. We want to go to solid state Dyson solar cell. So solid state, we need iodine. Iodine is a good electrolyte. So we make a polymer with iodine and make a solar cell. So when you make a polymer and make a solar cell, we get maximum of 6% efficiency. We can get a 6% efficiency. Okay, that's the most important point we do actually. So we choose some polymers and make a solar cell actually. So we take a polymer, polyepichlorohydrin, and we mix with the polymer some organic compounds, benzidine. This is the structure of benzidine actually, a colorless compound, and some fillers because we need to fill to make him a dry one. Okay, solid state. We add some fillers and make a polymer sheet, membrane, etc. like morphology, and we get a polymer membranes or polymer electrolyte actually. So what happens here? I told the preparation solar cell, step 2 and step 4, that is the cat on the wall, come back to the ground state. So this compounds, these compounds can avoid. The benzene is a colorless compound. When we get the light energy, it forms a radical. It forms a radical blue color. So dye molecule get absorbed. Also this form radical in the in situ. So this also absorb light energy and give efficiency more. Very important here in this case. I told, remember the first step, dye molecule goes to the conduction band and comes to the downside black one, or comes to the electrolyte green one. So this compound, when used as polymer electrolyte, what happens here? This dye molecule comes here, it once again pumps electrons. You can see here, this comes to ground state. Liquid electrolyte iodine won't react here because we are not using iodine here, we are using an iodine mixture actually. So this electrons comes and react with your benzene molecule and push the electron to radical, diradical, etc. So once again this pushes the electrons to the conduction band. So once the electrons come back, the failed electrons is also pushed back to the upper state and then return back to the circuit actually. So we get a good efficiency can be achieved. That's the advantage of your electrolyte with the benzene molecule, etc. So people can ask, sir, why you choose benzene molecule? Why not we can use any other material actually? So we make this one is a organic hybrid. We can say it's a polymer organic hybrid solar cell here. So people can ask, why not organic material? So why not we can use inorganic material or etc. So we know this efficiency we get efficiency of around 3.23% we can get efficiency. I can show you. So 3.43 efficiency we can get by this method. So we use your FTO, TO dye with a polymer electrolyte, we get efficiency of 3.43 in our lab conditions actually. Okay, that's important point. Okay. So then people may ask, so why use only your benzene? We can use other material also. So we are teaching classes now. When you teach classes, we can think which compound is better. Then we prepare ytterpolytungstic acid. This is one of the inorganic material. In the MSc level, you can teach ytterpolytungstic acid. So that material we mix instead of your benzene. Ytterpolytungstic acid is a colorless compound. When you apply light energy, it forms a new compound called ytterpoly blue, which also absorbs light energy around 760 nanometer. So we use this compound to make a new solar cell, and we get a good publications also comparatively to this one actually. That's also we did actually. Okay. This is the polymer. Now you know people when I am young, we always take bubble gum, okay? But nowadays we don't use bubble gum, we use centrifuge, okay? So what happened now? I said liquid electrolyte. Liquid electrolyte is purely liquid. Bubble gum like a polymer electrolyte, solid state, rough, okay? Bubble gum is rough. But a centrifuge is jelly type. So what happened now? We make a new polymer, okay, and inside will be jelly form. We make a jelly electrolytes. We make a jelly electrolytes actually, and then we make some efficiency. So that also we change. Instead of the pure solid state, we form a gel polymer electrolyte and we make a solar cell also. That also we did conditions, we changed one by one and get the good efficiency can be attained. That's the work we are doing actually. So I change your TaO to particle bed tube, dye molecules and electrolyte. And the last one, platinum. So platinum is a counter electrode, okay? Platinum is a counter electrode. So how we can change? Platinum is a counter electrode, how we can change actually, okay? So platinum is a good catalyst. We have to talk about when the catalyst means work function, okay? How the people can work. Platinum has a work function of 5.43 electron volt, which can has a good work function, can do better than any other compound, any other carbon, okay, carbon nanotubes, etc. Platinum is a good work function, so you can convert all the electrons and volts to a solar cell efficiency. So people can use platinum. But platinum has very expensive material, okay, very, very expensive material. So how can we can replace this one? So we want to replace this material equivalently. So we want to do the last work in this year, replace the platinum by different materials. So when we platinum, people say graphene, carbon nanotube are the best materials. So we also try carbon nanotube and graphene, okay. So graphene is like a mat. When you roll it, you can get a nanotube. A nanotube we can unzip, we can get a graphene nanosheets. So graphene is the strongest material equivalent to the power of your elephant. So we can use this compound, flexible, etc., stretchable, etc. So we can make a solar cell using a carbon nanotube and graphene, etc. So this is the carbon nanotube. So we can see the image actually. So they make a solar cell, platinum 12%, approximately 11%, single wall carbon nanotube around 9%, carbon different form, carbon filament, carbon nanoon, okay, activated carbon, just activated carbon here, low one. So we get different carbon morphology change, we get a different efficiency. But the carbon has drawback. Once again, carbon is highly pollutant. People can, even the carbon powder, they can found by Robert, I can forget the name, who got Nobel Prize. He died because of the carbon inhalation. So in that case, carbon has drawback, so we don't want carbon. And we are in India, so getting carbon at the time in 2010 or 2015, very expensive for us actually. So we dropped it actually. We want to make a cheap material. So how to make a cheap material actually? Okay, we think here, prepare a copper oxide nanorod. So this is very simple. Okay, any chemistry lab, you have a beaker and you have a copper sulfate solution there actually. So we take a copper sulfate solution in a beaker and maintain the pH conditions and make a copper oxide nanorod. Okay, that's the one we can notice actually. So we take a copper plate, just copper plate, and dip it in a solution of ammonia, copper sulfate, ammonia conditions, high pH, ammonia conditions actually. First copper reacts with ammonia to form tetramin copper complex, which will be a blue color one, and goes on reaction, its color turns to a dark blue, and finally it forms a copper oxide, black color precipitate can form. It forms a black color copper oxide. So we say copper oxide, simple say copper oxide. So we have to think copper oxide is everyone can do, even a technician in laboratory can do this one copper oxide. What we do research, sir? When we look into the TEM, yeah, very interesting images we can see. Just change the pH conditions of copper ammonia complex 9 to 14, just change the pH. We see the copper growth will be extremely different. You can see 10 images. So this images will be wrong rods. Copper shows in wrong rods can be formed at different pH conditions. This makes the interesting of copper oxide. Very cheap material. Just in the laboratory we change the pH and we get a copper oxide nanoparticle which shows a long rods in this TM. So we need instruments. When you have instruments, we can see what we can do. So that's the advantage where copper oxide show long rods. So we can get this, measure the rods also, very long one in TM, and make a solar cell. So what we do previously, TiO2 tubes we need, but we change the other side, platinum, instead of platinum sheet, we make copper oxide nanorods. So this is the one. And copper is a P-type semiconductor, that's a very important type. N-type P-type, TiO2 is N-type semiconductor, copper oxide P-type semiconductor. That's maybe a simple case. So TiO2, dye, electrolyte, and copper oxide, N-type P-type junction was there. So wherever the electron recombine, copper can take this one and avoid the electron hole regeneration. That means holes are separated, electrons are separated here by copper oxide. That makes your solar cell a good efficiency compound. That's the advantage of your very cheap material. You can see just you take a copper plate and dip in the ammoniacal solution for high pH conditions, we get your copper oxide nanorods. A very simple work. We can publish this one with this is the current we can get, this platinum, this is one with copper oxide. We can see pH we change from 11 hours to 12.3 at time of immersion of copper plate from 96 hours to 14 days. We get different efficiency can be attained. Very less efficiency, but we can see laboratory conditions 1.3 to platinum, but we get 0.29. But cost will be very small. Okay, peanut actually we can say peanut of cost. That's the advantage of your copper oxide compared to other material. So once we do this one, we have a very innovative work like this copper oxide. We want to do many materials like this. This is your TiO2 coated glass. On FTO we can coat TiO2, you can see a uniform coating, and this is a dye coated plate on surface, and this is your platinum coated, you can see transparent one, and we make a cell, single cell in a laboratory like this, but we make a big cell also, we make a single cell laboratory like this actually. Okay, instead of platinum I told we prepare your copper oxide, but copper oxide also we use copper metal actually, so we may say there may be some problem in the copper metal actually, so we want to make a counter electrode and make a TMS. What is TMS? We call transition metal oxides. We want to prepare transition metal sulfates a compound. This is very interesting for us when you want to prepare a transition metal sulfate compound instead of platinum, that was cheaper material, we can get a good efficiency can be obtained. So we want to make a transition metal sulfates in our laboratory to make a counter electrode. We make a different counter electrodes instead of platinum actually. So we take a hydrothermal method. Just this is the hydrothermal container with a Teflon container inside. First we take ammonium aldate and add thiourea. We add thiourea. So first this is the one first reaction. Ammonium aldate with thiourea and water. Simple reaction. Okay. We get a hydrothermal conditions, temperature 160 to 200 degrees Celsius. We get a black color powder. We get MOS2 nanosheets. Second one, what we do, we prepare cobalt nitrate and thiourea. Nickel nitrate and thiourea we can do. And combine this cobalt nitrate and nickel nitrate both with thiourea, that other one. And next one, we combine this ammonium aldate, cobalt nitrate, other one. Ammonium aldate, the aldate sulfate, cobalt sulfate. And cobalt sulfate, nickel sulfate. The last one, ammonium aldate, cobalt, nickel, everything we prepare sulfate. So we prepare some different morphology conditions and we see the SEM images. Very interesting for us actually, preparation is very simple. Only when we see the SEM images and TEM images, we have a interesting morphology we noticed when we prepare the compound actually. So MOS2, this is MOS2 XRD image, nothing changes because MOS2 we are not calcinated. You can see this, we are doing only room temperature 160 200 degrees Celsius, no calcination. So it can give a XRD amorphous form. You can see XRD will be mostly disturbed, amorphous form actually. And MOS2 sometimes not connecting much better, so we can mix something with graphene. So graphene also reduced graphene we noticed here, XRD, you can see. So first we give a SEM image, you can see the morphology, flower morphology we can notice. Without graphene, this is without graphene. With graphene we have some sheets will be there, graphene sheets are noticed actually here. So this is low field SEM actually. So we want to check this one with the field FESEM. So FESEM, we look in this one, the same compound here, we can notice this one by different morphology can be noticed. We can notice here different morphology. So we can see here a flower shape or sheet morphology can be noticed this compound actually. So when you look TM, the same surface morphology in the TM. TM also same surface more sheets are there actually. And IDEX, we can see the compound shows molybdenum, sulfur and some carbon. This is because we are coding the sample in the carbon system. We can get a copper foil or copper TEM image rods will be carbon will be done. So only pure molybdenum sulfate can be noticed here this compound. So molybdenum sulfate forms the flower morphology images. So that's an interesting compound we do actually. Very important. Now we did this one material. We have checked this compound has good catalytic activity similar to platinum. So platinum we do cyclic voltammetry. Tomorrow we can teach you how to do cyclic voltammetry. So we do cyclic voltammetry. We can see the compound platinum black one. There's a peak here, anodic and cathodic peak. The difference between your oxidation reduction peak will be 0.59 volt means is reversible potential. So the platinum shows almost this peak 0.59 volt. It may be your good reducing and oxidizing agent, so it may be cyclic compound actually. When you do molybdenum sulfate and coupled with the RGO also almost same peaks are noticed. So these compounds have good catalytic activity similar to your platinum, which shows a good catalytic activity. That's the important point we can understand actually. So we calculate your impedance, we do impedance and formed your sheet resistance and short-term resistance and your peak potentials we calculate here. Is equal to almost same. You can see platinum has 0.48 peak potential and your molybdenum will be 0.68, RG will be 0.482. So it will be, this two will be nearby 480 and 482. So we think this two may be better efficiency. So compared to MOS2, it shows a better efficiency can be noticed. And Tafel plot we do just to say the compound has undergo oxidation reduction properly and we are implying the compound has good catalytic activity can be done. Once we confirm this one for sample and we make a solar cell with the platinum molybdenum sulfate as a counter electrode and we get an efficiency of around 6.8%. Current you can see current will be millivolt, 800 millivolt voltage and 20 milliamps current. We can see previously we can show only 4 milliamps or 2 milliamps actually. We can get 20 milliamps current actually. Platinum is 15 we get in laboratory, but your MOS2 and MOS coupled RGO we get 20 milliamps current actually we get. That's the advantage of your MOS2. Transition metal sulfates can give a very high efficiency can be formed. So that's the scenario we maintain here. We get a good one. After this we do IPC. IPC is the one because the compound shows a good instant forward current efficiency. We found the compound so 30% of stability will be there, actually absorption will be there. So it has a good stability can be noticed. That's the advantage of the compound MOS2. The first material is MOS2, we can done. Okay, second I coupled with the cobalt sulfide. Okay, cobalt sulfide MOS2. Don't worry about XRD. Is MOS2 pure cobalt sulfide and composite will be here. Okay, we can notice. But don't worry about this compound. We want to see SEM. See, the image will be very interesting. Previously we have only sheet image, but when you couple with your cobalt sulfide, we get an image like this. We call fin balled image. We call fin ball, not fin rope. Rope will be, if you come Kerala, you know they will have a rope actually, coir rope. We call fin balled image can be obtained. We see the image will be like a fin balled image. So this is a prediction we give, and we see the compound as a good image. So that's the advantage of your molten sulfide, cobalt sulfide forms a fin balled image. The morphology is entirely different compared to normal one. That's the advantage of this material actually. We check your CV studies, kinetic activity, impedance, etc. So every time we do platinum fresh image, so the value may be different. Previously 480, now 497. So cobalt sulfide is nearby, but molten cobalt is 404. So this may be lower than peak potential compared to pure platinum. So we do the solar cell fabrication technique and find almost 20%. Current density will be 20, voltage will be 760. Previously 900, it decreases here when you put cobalt 763. Efficiency will be almost same 7.8. So your molten sulfide, cobalt sulfide shows a good image can be obtained. So molten image, molten we want or cobalt, which is better. We want to prove whether molten is better or cobalt is better. We compare. So to compare this actually we remove the molybdenum and put instead of cobalt and nickel, third one, we put cobalt and nickel. We put cobalt and nickel actually. The nickel has good conducting compared to molybdenum. So XRD, don't worry about XRD. Okay, we go to this one. Because of cobalt, it shows a twin ball structure. Since nickel is there, nickel shows only a broken nanosheets. You can see here, it forms broken nanosheets and nanowires morphology. Nickel forms a broken nanowires. Cobalt will form a twin ball. So these two mixture of morphology we can notice. So images are very, very interesting images we can notice here actually. Okay. So this compound, EDAX also same. CV also almost gets same value. So CV you can see the peak potential 597. It is 383 only. So nickel sulfide cobalt sulfide peak potential is somewhat different compared to pure nickel sulfide pure cobalt sulfide. Therefore, this compound we can do solar cell fabrication and find the compound get efficiency of 7.9, 16.1, 7.9. So nickel cobalt is less compared to molten cobalt. So we feel molten cobalt is better compared to nickel cobalt actually. Third, we want to combine all the three combinations, ternary combinations. We do ternary combinations, molybdenum, cobalt, nickel. So we do molybdenum, cobalt, nickel here, XRD remove. So we do molybdenum, cobalt, nickel. Cobalt will be like this one, and your molybdenum will be like a flower morphology. You can see flower morphology. You can zoom it like a flower morphology. And nickel will be a broken rods. You can see broken rods will be here like this. So all the morphology are retained in this one. So we get a bulk image. We get here bulk image, a very bulk image actually. So images are extremely good compared to normal one, and we notice the compound. Okay, just CV studies, platinum and compared to cobalt, it's almost same cutted actually. So we can use this compound as a good kinetic material for our applications. So we get a current of 824 millivolt and 15.7 milliamps current actually, efficiency of 7.8. So we find that replacing the platinum by all the material, we get a good efficiency can be noticed. So that's the advantage of it. We changed all the concepts of your solar cell, like your TiO2, dye, electrolyte and your counter electrode, and we get different morphology can be noticed. That's the advantage of your system actually. So now, what happens now? So target is to make a big material. Target is we want to make a bigger size material actually, bigger size material. Small size we do, we want to see a bigger material in our laboratory conditions. So this is we used a FTO glass, not this one. This is I get from Dr. Jagdish. In the lab only they do this flexible one. So we do pi cross pi 10 cross 10, 15 cross 15 in our laboratory, and maybe this video works. I think I have to click. Sorry, it's not working now here. Sorry? Escape. No, is image next one. Okay, maybe the video is moved actually, I know. In another computer. This one. Okay. Yeah, I'll show you later tomorrow. So this video will be working, and we get this one very important here in this case. We do this one, the straight line. Okay, series connection, parallel connection only we do, and the watch will be working actually. So we feel instead of series connection, we can change this morphology like a straight line. We do in laboratory like a zigzag pattern, like this. So this pattern can make yourself get more efficiency. We get, you can see 645 is the voltage we get, and current also good actually, you can notice. That's advantage we can do in our laboratory, different types actually. So we have fabrication instruments in the laboratory. We'll show tour for you, laboratory, and then we can identify this one actually. And we make a big cell, and we don't have solar cell meter big cell. We go to other laboratory and put a big cell, and we find how it works in the laboratory and how long it will work, see the flexibility, etc. The concept actually. Okay, so what happened now? This is the glass place we are do. So we have collaboration with Dr. Jegadesan lab. So where they have a flexible preparation. So this is the one they use films. You can see they can by gravure printer film. They use the gravure printer film actually. Like they have instruments here. We don't have such instruments. This instrument they have in the Australia. So they make a big sheets. They make a big sheets like this one actually in the conditions. We don't have such facilities here. So they are the one, and they give a free sample for me when I visit University of Melbourne during last year actually. So this is the flexible film can prepare, and Australia they can make this film as a tent, etc. Conditions actually. So this is one of the they have model. They put like a big building in Australia actually, Newcastle. And if you go to Japan, they have like in the shirts and pants they can use this one, and they can charge the phone. And this is the flexible one we can use tent for military people. And this is Great Cell Group. They are selling this one. Okay, 60 pounds, 60 euro. Okay, approximately 5,270. This bag solar cell will be, they can put in the backside actually. That's advantage. So this is the model. So we also want to try, but in Indian conditions very tough. We can do extreme case actually. Okay. So this solar cells, last we can say that if we talk about the solar cells actually, okay, it may be a 1996, 1999 they started the first work. 2026 now, almost 30 years old, 30 to 35 years old. So we don't want to work this one. This is all old work. We don't want to work this one actually. Okay. So we want to move to perovskite solar cells. So what is perovskite solar cells? What is the use actually? Okay. So when we start this one and drop to perovskite solar cell, we have initially drawback is people say why dyes in solar cell? Dyes have problem, toxic. They want to replace dye by perovskite material. So perovskite material nothing but inorganic, purely inorganic material actually. So this is the ready-made available from the various institutes, EPFL. They prepare TaO2 plate, FTO, TaO2. Instead of the dye molecule, they use a perovskite. Lead tetramethammonium iodide. This is the compound used actually, perovskite material actually. It's a yellow color compound and not stable. Very important, this compound is not stable actually. And they use this old transmitting material, maybe a fullerene or spiro compound, etc. These are very expensive materials. So these are very expensive materials. It is not stable, it is expensive, but you can see according to European conditions, they can make stabilization because they have all facilities. It needs a glove box. For Dyson solar cell, we don't need any glove box, but here it needs a glove box, etc., to get efficiency of 12% or now they get 24%. They used volt transmittal polytriarylamine or fullerenes or spiro compound to get a good efficiency. So saying this one, we want also, MP is called mesoporous TiO2. Okay, mesoporous TiO2, this is black TiO2, they get TiO2 different form, black TiO2, mesoporous TiO2, lead aluminum compound, volt transfer material and gold electrode, all they can use and they can make. So what we want to do, we also want to start this work actually, so using this compound, so we do this in our laboratory conditions actually, okay. So we also do the same thing, FTO, TiO2 and lead aluminum iodide, spiro and silver, and we did this one with the help of IIC Bangalore, and we published paper in IEEE, but we don't publish the concept of perovskite solar cell because perovskite is 24% they get actually, but we get around only less percentage. We get only less percentage, like maybe 10% or low actually. What we do, we change the concept. We do the noise pollution because solar cells of noise will be there. How to avoid noise? If instrumentation companies, instrumentation people know, in the instrument if you use noise is coming actually, so same noise is coming solar cell. So this instrument material we want to reduce the noise actually, and then we want to see the effect how it comes. So that's the application we published in IEEE in 2018. The initial work. So this is known compound, okay, this is known compound, all known. So we just published the noise factor in IEEE in 2018. Now, we think this is a problem. We think this is a problem for you, yellow compound, and we need a glove box. It's not stable. Okay, so we want to replace this material in our laboratory by different molecules. So we started working in different method called LARP assisted synthesis of cesium bismuth iodide. So we take a compound cesium iodide, bismuth iodide and DMF, and mixing toluene we get a compound cesium bismuth iodide. So this work we initially prepared compound and we collaborate with VIT Vellore initially, but we don't, according to Indian scenario, we don't get good efficiency actually. So we are not able to collaborate with them actually. Then we drop and then we give this material to once again to Dr. Jagadish, and there in Australia they make a solar cell. They use ITO, nickel oxide, and this perovskite material they quote here actually, and fullerene and BCP, there's another material they use here in this compound, voltage material, and then silver, they get a compound. So this compound cesium is very important here. In normal condition, without calcination, it becomes orange color. And the amorphous, see the image are not good actually. When you calcinate, then only it forms perovskite. That's very important here. We generally do with same material, colorful made, we don't get any image, but Dr. Jagadish uses material and he calcinated different conditions actually, and then he convert the compound to perovskite form, and once he get perovskite, then he make a solar cell, he get efficiency of very less initially, we can say 2.3%. So this is the one we published with him with the RSC advances in 2023. So we can see we start 2018, 23 only we published our first new work in this area of paper actually. So like this we are doing also now, continuously we are doing some material and we are trying to get good efficiency in the near future. That's our work we are doing actually. So this all work will be instruments for Dyson solar cell funded by DST. DST gives a very big budget for me, 1 crore Indian money actually. All screen printing instruments, etc. So I have to thank them, CSR, and also CSR, DST, CSR, Ministry of Environment, Forest and Spark, and now GIAN, and mainly my students, Dr. Vijaya, Dr. Mr. Siddiq, and Dr. Agalia, who do a lot of the works here in this case. So they are the people do a lot of works in this morphology changing method actually. So I have to thank them for this innovative work. And the SEM, TEM mostly we did in Taiwan, not in India. Some work we do in Amrita, and most of the work we see the images will be from Taiwan. That's why you get a clear images actually compared to other material. Taiwan and as well as the Australia, University of Melbourne. Dr. Ashok Kumar and Jagdish may help us to do a lot of most images. So that's the one I have. And this is the just for market the silicon solar cells panel here. So I can put in sunlight, it can rotate like this. You can see very small motor here. You can just put in here, it can rotate actually. You can see this maybe, but I don't know, here it is. Yeah, you can see here rotate. Silicon solar cell will rotate very easily compared to but similarly we purchased one local one. This is Dyson solar cell. This is Dyson solar cell, very small images here actually. So this will rotate this one, but now something happened actually, I know long back. So I will try to arrange something. So this all we have demo pieces in our laboratory to show a good solar cell applications. So we will give you more demos, solar cell demo Thursday afternoon actually. So how to fabricate TO2, how to make your etc. We'll explain, and then we go with the next topic actually. Okay. So thank you one. So if you have any questions, I'm happy to answer your thing actually. Any questions? If you have, I'm ready to answer you. Yeah. Sorry? DM of year. See, generally organic compounds, this cesium or bismuth added form, it won't soluble in water actually. So in case we need organic solvent is better actually. The LAP is called ligand assisted lap is in this method. So where we can use as organic solvent mostly. Common organic solvent for both the materials, cesium and bismuth. So this will soluble only in DMF actually. Any questions? Okay, I think so. I explained you most clearly. I think hope you can understand. Anything you have doubts personally, you can ask me at any time. Doing preparation also we will do explain actually. Okay. So today afternoon we have another lecture by Dr. Jegadesan, and then we have a demo class, UV and spin coating etc. We will demo here in this laboratory. But this is today's class actually. Okay. Thank you one and all for attending the lecture.